All right, after a quick wardrobe change, we're back, and we've got a 50 Newton force applied to the box at 37 degrees above the horizontal as shown. The coefficient of kinetic friction between the box and the plane is 0.4. Draw the other forces acting on the box. Forces, free body diagram, Newton's second law equation. Let's do it. We'll start with the easy one. We know that is mg. And to save on our calculations later on, let's go ahead and plug in these numbers. 10 times 10 is going to be 100 newtons. Going down, we have 50 newtons here. Our frictional force goes like this. I don't know what that is just yet. And then we have our normal force. Normal force is not the same length as our weight. Remember, our normal force plus this vertical component have to equal the weight. So our acceleration is to the right. So we have frictional force is parallel, normal force is perpendicular, weight is perpendicular. This 50 Newton is neither, so we're going to resolve it into its components, where we have a horizontal or parallel component, and we have a vertical or perpendicular component. And there's our angle. So this side will be adjacent because it's touching the side. So it's going to be 50 cosine 37. And then this side will be the opposite side, so that will be 50 sine 37. 50 sine 37 is going to give us 30 newtons here. And then this one here, 40. So this component is 40, this component is 30. Okay, let's get to it. Write two equations that relate the forces on the box. Well, we have parallel forces and we have perpendicular forces. Parallel to acceleration and perpendicular to acceleration. So let's do it. Let's go ahead and start with our net force that is parallel. Stuff that makes it go is going to be this 40 newtons, which is going to be the 50 cosine 37. So we can just call it the parallel component of the 50, or we'll just go ahead and put in that 40. Minus the stuff that holds it back, our frictional force, equals mass times acceleration. Are we moving in this direction? Yes, we're moving along this plane, so we're going to leave it at that. How about the net force that's perpendicular? Perpendicular forces, the stuff that makes it go, we'll do up. So we have Fn plus this piece right here, 30, equals, minus. Those two are in the up direction. And then minus stuff that holds it back, 100 will equal 0, because we're not floating and we're not sinking. What is the normal force acting on the box? This equation that we just wrote is going to come in real handy for this. Fn plus 30 minus 100 equals 0. Add 100 to each side, subtract 30, and we're going to get Fn equals 70 newtons. Frictional force, same thing. 40 minus our frictional force equals ma. Subtract frictional force and then subtract mass times acceleration on this. We don't know our acceleration, do we? Oh, nuts. We can't do that. Okay, so what else do we know about friction? Well, let's see. We know that our frictional force equals mu times Fn. Oh, and we just solved for Fn. And we have mu, which is 0.4. So 40% of 70 here. Our frictional force will equal 28 newtons. Cool, right? Now it's asking what is the acceleration of the box. Now we can use this equation because we have frictional force. We can just pop that in there, and it's going to be 40 minus 28 equals mass times acceleration. So I'll go ahead and rewrite the equation for you, though I don't need to. 40 minus 28 equals mass is 10 times acceleration. 40 minus 28. Yeah, 12. Divided by 10 equals A. A equals 1.2 meters per second squared. That, my friends, is pretty cool. We were able to just completely dissect this situation where we were given relatively little information. We're talking about a friction problem with a force at an angle, and we figured out all of this. Not using any special tricks or anything like that. It's just taking our time, logically thinking about the steps, and does it make sense?